December 15th, 1944. A laboratory in the Kaiser Wilhelm Institute for Physics, Berlin. Dr. Werner Osenberg leaned forward, magnifying glass in hand, studying the scattered components spread across the laboratory table. The fragments had been recovered from an unexploded American artillery shell that had fallen near German positions in Italy. His colleagues, some of Germany's finest electronics experts, gathered around in silence, their faces illuminated by the harsh overhead lights. "Impossible," whispered Dr. Kurt Diebner, shaking his head slowly. "The Americans cannot have miniaturized a radio transmitter and receiver to this degree. And to withstand the shock of firing? It defies everything we know about vacuum tube technology." Reich Minister of Armaments. Albert Speer stood in the shadows behind them, his tall frame rigid with tension. He had seen many weapons, participated in countless technical evaluations, but the expressions on the scientists' faces told him something was different this time. "What exactly am I looking at, gentlemen?" Speer finally asked. Osenberg turned, his face ashen. "Herr Reichsminister, this is an American proximity fuse. We've suspected they existed based on field reports, but this is our first intact specimen. It contains a miniaturized radio transmitter and receiver that detects when the shell is near a target and detonates it automatically at the optimal moment." "We have similar projects," Speer replied dismissively. "No," Diebner interjected. "Nothing like this. Our proximity fuses are primitive compared to this design. The Americans have placed a complete radar system inside an artillery shell, made it rugged enough to withstand 20,000 G-forces upon firing, and mass-produced it in quantities that suggest they're supplying their entire army and navy." Speer picked up one of the vacuum tubes, smaller than his fingernail. "Could we reproduce this?" The silence that followed was more alarming than any answer could have been. Finally, Osenberg spoke. "Theoretically, yes. Practically, no. We lack the industrial capacity for miniaturized vacuum tube manufacturing on this scale. The precision equipment alone would take years to develop." In that moment, as he stared at the tiny technological marvel in his palm, Albert Speer would later write in his memoirs that he understood with sudden crushing clarity that Germany had already lost the war. Not because of any single battle, but because they were facing an industrial colossus that could mass-produce technological miracles, while Germany struggled to manufacture even basic equipment. "The Americans," Osenberg added quietly, "are estimated to be producing 50,000 of these fuses every day." The race for proximity. The story of the VT, variable time fuse, later known more commonly as the proximity fuse, began years earlier in a very different setting. On a humid July morning in 1940, Dr. Merle Tuve paced the length of his office at the Carnegie Institution in Washington, D.C. British scientists had just arrived bearing urgent requests for American scientific assistance. The Battle of Britain was raging, and German bombers were overwhelming conventional anti-aircraft defenses. The fundamental problem was brutally simple. Anti-aircraft shells had to explode within 70 feet of an aircraft to have any chance of damaging it. Using conventional time fuses, this meant gunners had to estimate the exact altitude of enemy aircraft and set fuses accordingly. The result was a hit rate of less than 1%, an exercise in mathematical futility that consumed enormous resources for minimal effect. What was needed was a fuse that could detect when it was near an aircraft and detonate automatically. The British had explored several approaches, including photoelectric cells and acoustic sensors, but nothing had proven practical under combat conditions. Tuve, a physicist who had worked on proximity detection for meteorological research, immediately grasped both the challenge and the opportunity. Within days, he had assembled an extraordinary team of scientists from America's most prestigious institutions. The National Defense Research Committee authorized the project with an initial budget of $400,000, a staggering sum for a single component in 1940. The pressure was immense. "We were acutely aware," Tuve later recalled, "that every day we delayed meant more Allied planes shot down, more factories bombed, more lives lost. Our enemy was not just the technical challenge, but time itself." Early designs explored multiple approaches simultaneously: photoelectric cells, acoustic sensors, capacitance detectors, and radio proximity detection. By late 1940, radio detection emerged as the most promising avenue. The concept was elegant. A tiny radio transmitter in the nose of the shell would emit signals that would bounce off nearby objects. When the reflected signal reached sufficient strength, indicating proximity to a target, the fuse would detonate. The theory was simple. The engineering challenges were monstrous. First, vacuum tubes, the only electronic amplification technology available, had never been designed to withstand the shock of being fired from artillery pieces, which subjected them to forces up to 20,000 times that of gravity. Second, the entire system had to function on battery power for up to 60 seconds after firing. Third, it had to be small enough to fit into a standard artillery shell. Fourth, it could not detonate prematurely and endanger friendly forces. And finally, it had to be manufactured in enormous quantities at a reasonable cost. Any one of these challenges would have been considered nearly impossible before the war. The combined requirements seemed like scientific fantasy. Richard Crane, of the University of Michigan, one of the project scientists, wrote in his journal, "We are being asked to achieve in months what would normally take decades of incremental development. Many of my colleagues believe we are pursuing an elaborate technical fantasy." By September 1941, the team had produced the first working prototypes. The breakthrough came in the form of specially designed vacuum tubes, smaller than anything previously manufactured, with internal structures that could withstand enormous G-forces. The tubes were suspended in special shock-absorbing compounds and connected by flexible wiring rather than rigid connections. Even as the technical challenges were being solved, an even bigger question loomed: how to manufacture such a complex device in the quantities needed for war. The most pessimistic estimates suggested America would need millions of proximity fuses, more than the total number of vacuum tubes produced in America before the war. The arsenal of ingenuity. When Japanese bombs fell on Pearl Harbor on December 7, 1941, the proximity fuse project gained unprecedented urgency and resources. The U.S. Navy, facing the threat of Japanese air attacks against its fleet, became the primary driver behind rapid deployment. Admiral William "Spike" Blandy, chief of the Bureau of Ordnance, visited the project laboratory in January 1942. After witnessing a test in which proximity-fused shells consistently detonated within lethal range of target drones, Blandy reportedly slammed his fist on the table and declared, "Gentlemen, that is the biggest advancement in naval warfare in my lifetime. I want 30,000 of them, and I want them yesterday." The scale of the challenge was staggering. The most complex, mass-produced electronic device before the war had been the radio, containing perhaps 5 to 10 vacuum tubes. Each proximity fuse required specialized miniaturized tubes, precise resistors and capacitors, and complex circuitry, all packed into a space the size of a grapefruit and engineered to withstand forces that would flatten an automobile. The solution came through an unprecedented mobilization of American industry. 5 major corporations, Crosley, Eastman Kodak, Raytheon, RCA, and Sylvania, were enlisted to manufacture components. None had previous experience with military fuses, but all had expertise in mass-producing electronic components. Crossley Corporation, better known for manufacturing refrigerators and radios, converted its entire Cincinnati plant to fuse production. Within months, assembly lines staffed primarily by women workers were producing tens of thousands of fuses daily. As one supervisor noted, these women, many of whom had never held a soldering iron before the war, were building devices more complex than anything most electronic engineers had created before 1940. The statistics were staggering. By mid-1943, American factories were producing 40,000 proximity fuses per day, more than Germany manufactured in the entire war. By war's end, over 22 million would be produced at an average cost of $32 each. The scope of the effort remained among America's most closely guarded secrets. The project employed over 40,000 people across multiple states, yet security was so tight that most workers had no idea what they were building. Components were manufactured at separate facilities, with final assembly occurring at secure integration plants. The secrecy extended to the battlefield. Commanders were under strict orders that no proximity fuse could be used where there was any risk of an unexploded specimen falling into enemy hands. For nearly 2 years, this remarkable weapon remained in storage while conventional ammunition was expended at enormous rates. German intelligence remained largely unaware of the project. A captured Luftwaffe intelligence assessment from 1943 concluded, "Americans have made no significant advances in anti-aircraft technology. Their focus appears to be on quantity rather than quality." Meanwhile, in Germany, similar projects struggled against increasingly dire material shortages. Dr. Walter Dornberger, who oversaw many of Germany's advanced weapons programs, later wrote, "We began developing radio proximity fuses in 1940, but our prototypes were bulky and unreliable. We could never overcome the miniaturization challenges, and as bombing intensified, we simply lacked the industrial capacity to pursue full development." In a tragic irony, German scientists actually possessed the theoretical knowledge to create similar devices, but lacked the industrial base to implement their designs. A prototype German proximity fuse developed in 1943 was the size of a small suitcase, far too large for artillery applications. The contrast illustrated a fundamental difference in approach. Germany had concentrated on developing a smaller number of wonder weapons, the V-1, V-2, and jet aircraft, while America focused on perfecting and mass-producing technologies that could be immediately deployed. Wernher von Braun, creator of the V-2 rocket, later remarked, "In Germany, we pursued technical sophistication at the expense of practicality. The Americans pursued practical solutions that could be manufactured by the millions." The Test of Combat, January 5, 1943, HMS Scylla, English Channel. Commander Roger Hill stood on the bridge, his eyes fixed on the horizon where a formation of German bombers was approaching the Allied convoy his ship was escorting. Previous raids had proven devastatingly effective against ship-based anti-aircraft defenses. Conventional anti-aircraft shells required direct hits or perfect fuse timing, nearly impossible against fast-moving aircraft. Today would be different. In the ammunition locker below decks sat 50 shells fitted with the new American VT fuses, the first to be released for combat use at sea. The strict secrecy surrounding them had been maintained to the last moment. Gunners had been told only that they were special ammunition to be used against aircraft. "Commence firing when ready," Hill ordered as the first Junkers Ju-88 bombers came into range. The ship's 4-inch guns roared to life. The first salvo arced skyward, trailing smoke. Hill tracked them through his binoculars, expecting the usual frustration of watching shells explode harmlessly before or after passing the target aircraft. Instead, a flash erupted precisely alongside the lead German bomber. The aircraft shuddered, then rolled over and plummeted toward the sea, trailing smoke. Before the crew could celebrate this extraordinary luck, a second bomber was hit by another proximity-fused shell. By the end of the engagement, the Scylla had shot down 5 German aircraft with just 32 proximity-fused shells, an unheard-of ratio in naval anti-aircraft gunnery. In his action report, Commander Hill wrote, "The new fuses transform anti-aircraft defense from an exercise in futility to a deadly efficient system. It is not an exaggeration to state that they multiply our effective firepower by a factor of at least 5. Despite this dramatic success, the American High Command continued to restrict the use of proximity fuses to naval engagements at sea, where unexploded shells would sink without trace. The risk of the technology falling into enemy hands was considered too great to permit land-based use. This changed dramatically in December 1943 during the Allied landing at Anzio, Italy. German air attacks against the vulnerable beachhead were inflicting heavy casualties. With the situation desperate, General Dwight D. Eisenhower authorized the deployment of proximity fuses for the first time in land combat. On January 24, 1944, the 4 7-inch guns of the 240th Anti-Aircraft Artillery Battalion opened fire with proximity-fused shells against a formation of 24 Luftwaffe bombers attacking the beachhead. The results were spectacular. In a 7-minute engagement, 7 German aircraft were shot down, a kill rate 10 times higher than with conventional fuses. Sergeant William Ross, who witnessed the engagement, later recalled, "The German pilots were flying the same patterns they'd used successfully before. They had no idea what hit them. One moment we had a sky full of bombers, the next we had a sky full of parachutes and falling debris." The most dramatic demonstration came in the summer of 1944, when Germany launched its V-1 flying bomb campaign against England. These pilotless jet-propelled bombs presented an almost impossible target for conventional anti-aircraft fire. They flew at 400 miles per hour, too fast for accurate time-fused shooting, and carried a 1-ton warhead. The first week of the V-1 campaign saw hundreds of the weapons striking London with devastating effect. British anti-aircraft batteries using conventional fuses managed to shoot down less than 20% of the incoming threats. On June 17, 1944, American proximity fuses were rushed to the British defenses. The transformation was immediate. By the end of June, the success rate had risen to 46%. By August, it reached an astonishing 79%. German V-1 launch crews reported that fewer than 1 in 4 of their weapons was reaching the target. Field Marshal Gerd von Rundstedt, who had overseen the initial V-1 offensive, bitterly complained to Berlin, "Something has changed dramatically in the British defenses. We are now wasting resources and crews on a weapon that has become ineffective." What had changed was not just the technology, but the entire equation of air defense. A revolutionary device, produced on unprecedented scale by American industry, had rendered an entire class of German weapon largely impotent within weeks of its deployment. For German scientists and military leaders, the proximity fuse represented something even more significant than a tactical setback. It demonstrated that American industry was now producing advanced technology at a scale that Germany could not hope to match. The moment of revelation, February 17, 1945. Underground Bunker Complex, Berlin. The mood in the concrete conference room was grim. Albert Speer sat at the head of the table, surrounded by Germany's top weapons scientists, engineers, and military officers. On the table before them lay an array of American proximity fuses in various states of disassembly, some recovered intact, others reconstructed from fragments. "I need absolute clarity," Speer said, his voice echoing in the austere room. "Can we manufacture these?" Dr. Werner Osenberg, director of the Reich Research Council, cleared his throat. Herr Reichsminister, I have personally interviewed our top electronics manufacturers. The consensus is unanimous. We understand how they work. We can replicate the design, but we cannot manufacture them in any meaningful quantity. Explain, Speer demanded. Dr. Kurt Diebner, the nuclear physicist, leaned forward. The Americans have developed specialized mass production techniques for miniaturized vacuum tubes that simply don't exist in Germany. Each proximity fuse contains between 3 and 5 tubes smaller than anything we've ever mass-produced. Our engineers estimate it would take 18 to 24 months to develop the necessary production equipment, and that assumes no further bombing of our factories. What about our existing proximity fuse projects? Asked General Walter Dornberger, head of the V-Weapons program. Our designs are fundamentally different, replied Dr. Wilhelm Fennel from Siemens. We pursued acoustic and optical detection methods because we lack the capability to miniaturize radio components. Our prototypes are 4 times larger than the American device and still unreliable. Speer's face remained impassive, but those who knew him well could see the tension in his jaw. He picked up one of the tiny vacuum tubes, examining it under the harsh bunker lighting. How many of these fuses do our intelligence services estimate the Americans are producing? He asked. Field Marshal Wilhelm Keitel, chief of the Wehrmacht High Command, consulted his notes. According to our latest intelligence, approximately 45,000 to 50,000 per day. A murmur ran through the room. Speer set down the vacuum tube with deliberate care. That's more than we could hope to manufacture in a year, even if we diverted resources from other critical programs, he said quietly. And they're producing them daily. The silence that followed was broken only by the distant rumble of Allied bombs falling on the outskirts of Berlin. Gentlemen, Speer finally continued, we are witnessing something beyond a technical achievement. This device represents an industrial capacity that we cannot match. The Americans have not only solved an extraordinary engineering problem, but have made that solution available to every artillery piece in their arsenal. Dr. Abraham Esau, head of the physics section of the Reich Research Council, spoke for the first time. What's most remarkable is the integration of multiple technologies, the miniaturization of the vacuum tubes, the rugged construction, the power supply. Any one of these would represent a significant achievement. Together, they demonstrate a technical and industrial capability we severely underestimated. Colonel Erich Fellgiebel of Wehrmacht Intelligence pushed forward a folder. There's more, Herr Reichsminister. According to information from our agents, the fuse was developed in less than 2 years, from concept to mass production, and the factories producing them were converted from civilian manufacturing, refrigerator and radio plants, primarily. Speer leafed through the intelligence report, his expression darkening. The implications extended far beyond this single device. If America could accomplish this feat, developing a revolutionary technology and mass-producing it in the millions using converted civilian factories, what else might they be capable of? The Führer must be informed, Keitel stated firmly. And tell him what exactly, Speer replied, an edge in his voice. That American housewives are assembling sophisticated electronic devices that our finest engineers cannot replicate? That a nation we dismissed as technically inferior and industrially soft is now outproducing and out-engineering the Reich across multiple domains? Dr. Osenberg spoke again, his voice low but clear. Herr Reichsminister, there's a fundamental difference in approach we must acknowledge. We focused our resources on a small number of revolutionary technologies, the V-2, the jet aircraft, submarine technology. The Americans have perfected the art of making revolutionary technology practical, reliable, and mass-producible. The insight struck Speer with particular force. Throughout the war, Hitler had been obsessed with wonder weapons that would reverse Germany's declining fortunes through technological superiority alone. Yet here was evidence that the true wonder weapon was not a single device, but an industrial system capable of turning scientific concepts into battlefield realities at a scale Germany could not comprehend, let alone match. The proximity fuse is not merely a weapon, Speer later wrote in his diary that night. It is a perfect symbol of why we are losing this war. We sought a handful of miracles. The Americans have created an assembly line of them. Through their eyes. The revelation of American technical and industrial superiority affected different participants in dramatically different ways. Their personal accounts, preserved in diaries, letters, and post-war interviews, provide a window into the psychological impact of this moment of clarity. For Albert Speer, the proximity fuse represented the failure of his entire approach to managing Germany's war economy. Despite his reputation as a miracle worker who had dramatically increased production despite Allied bombing, he now confronted evidence that his best efforts were utterly insufficient. In a letter to his wife dated February 20, 1945, Speer wrote, "I have spent 3 years performing organizational miracles to squeeze maximum production from our factories. Now I discover that our enemies have been operating on an entirely different scale, manufacturing technological marvels as if they were tin cans. The disparity is so great it cannot be bridged by any organizational genius or worker sacrifice." Dr. Werner Osenberg took a more analytical approach. In a classified report prepared for the Reich Research Council in March 1945, he wrote, "The American proximity fuse demonstrates a new paradigm in warfare, the industrialization of scientific genius. While German research remains world-class, our inability to transition from laboratory to mass production at speed represents our greatest vulnerability." General Heinz Guderian, chief of the German Army General Staff, viewed the revelation through a military lens. In his post-war memoirs, he recalled, "The proximity fuse exemplified the American approach to war, the application of overwhelming material superiority through technical innovation. A German soldier with superior training and tactical doctrine now faced not only more American tanks and planes, but American shells that needed only to come close to be effective." Perhaps the most poignant reaction came from Dr. Abraham Esau, who had spent years assuring Hitler that German science remained world-leading. In a private journal discovered after his death, he wrote, "The proximity fuse has shaken my confidence in our technological superiority more than any other Allied development. It is not that they have created something we could not theoretically create, it is that they have produced it in quantities that transform theory into overwhelming battlefield reality." For the factory workers and engineers who had created the proximity fuse, the impact was quite different. Dr. Merle Tuve, who had led the development effort, later recalled, "We knew we were creating something revolutionary, but we had no idea how profound the psychological impact would be on our enemies. We were simply solving problems as they came, pushing through technical barriers because the need was urgent and the resources available." Ralph Baldwin, one of the key scientists on the project, described the development process. What made the proximity fuse possible wasn't just scientific ingenuity, but the seamless integration of academic research, industrial engineering, and mass production techniques. Scientists, engineers, and production managers worked side by side, solving problems collectively that would have been insurmountable in isolation. The contrast between American and German approaches extended to the factory floor. Esther Riley, who worked at the Crosley Corporation plant in Cincinnati, recalled, None of us knew exactly what we were building. Security was that tight. But we understood it was important. We had photographs of our boys overseas on the walls to remind us why every piece had to be perfect. We were producing 40 fuses per person per day by 1944. This production rate astounded German analysts when they learned of it. A similar German precision electronic device typically required 4 to 6 man-days of labor per unit. The Americans had reduced this to a single worker producing dozens daily through advanced production engineering and specialized tooling. The experiences of frontline soldiers provided the most vivid testimony to the fuse's effectiveness. Lieutenant James Conway of the 240th Anti-Aircraft Artillery Battalion wrote home in February 1944, "We have new shells that have changed everything. Before, firing at enemy aircraft was mostly noise and smoke with little effect. Now, we're bringing down planes with every few rounds. The Germans have started avoiding our firing positions entirely." From the German perspective, Luftwaffe pilot Hauptmann Karl Mittendorfer described the sudden change in anti-aircraft effectiveness. In early 1944, something happened to Allied anti-aircraft fire. Suddenly, shells were exploding precisely as they reached our formation, even when we varied altitude and approach. Flying became dramatically more dangerous overnight, and we had no explanation for what had changed. Strategy, the mathematics of industrial warfare. The strategic implications of the proximity fuse extended far beyond its immediate tactical impact. It represented a fundamental shift in the relationship between technology and industrial capacity that would define modern warfare. The raw statistics told a story of overwhelming disparity. By 1944, the United States was producing 50,000 proximity fuses daily, 800 combat aircraft monthly, 88,000 vehicles monthly, 500,000 tons of steel monthly. In contrast, German production for the same period averaged: no operational proximity fuses, 150 combat aircraft monthly, 20,000 vehicles monthly, 100,000 tons of steel monthly. These figures reveal more than simple quantitative differences. They demonstrate qualitative transformation through scale. American industry had reached a critical mass where quantity itself became a form of quality. The ability to equip every gun, every plane, and every ship with advanced technology created an overwhelming advantage that no tactical brilliance or fighting spirit could overcome. Major General Leslie Groves, who directed the Manhattan Project, observed, "The proximity fuse and the atomic bomb represent opposite approaches to the same problem." The atomic bomb was a single weapon of unprecedented destructive power. The proximity fuse was a small improvement applied to millions of conventional weapons, achieving strategic impact through ubiquity rather than individual power. This observation captures a crucial insight about American industrial military power. The United States excelled not just at creating revolutionary technologies, but at making them practical, reliable, and universally available to their forces. Admiral William "Spike" Blandy, whose advocacy had been crucial for the fuse's development, noted in a 1945 report, "The proximity fuse demonstrates that the modern military-industrial complex must excel at 3 distinct capabilities: scientific innovation, engineering development, and mass production." Germany maintained excellence in the first, struggled with the second, and failed catastrophically at the third. The mathematics of industrial warfare extended beyond production numbers to research and development resources. By 1944, more than 1,000 scientists and engineers were working directly on proximity fuse improvements, supported by another 40,000 workers in production. Germany's equivalent programs employed fewer than 100 scientists and had no mass production capability whatsoever. This disparity became self-reinforcing. American mass production created economies of scale that reduced costs dramatically. The first proximity fuses cost approximately $700 each to manufacture. By 1945, the cost had fallen to $32, less than many conventional mechanical time fuses. Germany, unable to achieve mass production, could never have realized such economies of scale. The difference in approaches was philosophical as much as practical. German weapons development prioritized technical sophistication and performance, often at the expense of reliability and manufacturability. American development balanced performance against producibility, willingly accepting good enough solutions that could be manufactured in enormous quantities. Dr. James Finney Baxter, official historian of the Office of Scientific Research and Development, observed, "The German approach to weapons development resembled crafting precision watches, emphasis on perfection in limited quantities. The American approach resembled automotive manufacturing, emphasis on good design that could be reliably mass-produced." This difference extended to human resources as well. The American Proximity Fuse program deliberately designed manufacturing processes that could be performed by workers with minimal training, many of them women with no previous industrial experience. German manufacturing relied heavily on skilled craftsmen whose training took years and could not be rapidly expanded. By early 1945, German leadership faced a stark reality. They were not merely being outproduced, but out-innovated in ways they could not counter. Field Marshal Albert Kesselring summarized the situation bleakly. "We find ourselves in the position of a skilled swordsman forced to duel against an opponent with a machine gun. Our technical skill and fighting spirit are rendered irrelevant by the fundamental inequality of capabilities." The proximity fuse represented a turning point in German perception of American capabilities. Before its discovery, many German leaders maintained the belief that American material superiority was offset by German technological and tactical advantages. After understanding the fuse and its production scale, this consoling fiction could no longer be maintained. Perhaps most significantly, the proximity fuse demonstrated that America's vaunted production capability was not limited to simple goods mass-produced through brute force industrial might. The United States had proven it could mass-produce sophisticated technology requiring precision manufacturing and complex electronics, the very areas where Germany had assumed unassailable superiority. Legacy of Revelation, April 30, 1945, Los Alamos, New Mexico. Dr. Vannevar Bush, director of the Office of Scientific Research and Development, stood before an assembly of scientists and engineers working on the Manhattan Project. As America's scientific research czar, he had overseen both the atomic bomb development and the proximity fuse program. "What you are creating here represents the ultimate extension of a capability we have demonstrated repeatedly," Bush told the assembled scientists. "The ability to transform scientific discovery into practical military power through the combined efforts of research, engineering, and American industry." Bush's statement captured the enduring legacy of the proximity fuse, not merely as a weapon that helped win World War II, but as a model for how modern nations would approach technological warfare in the decades to follow. The proximity fuse's development established organizational patterns that would define American military technology for generations. The close collaboration between universities, government laboratories, and private industry created what would later be called the military-industrial complex, a powerful innovation ecosystem that could rapidly translate scientific discoveries into battlefield capabilities. This model proved so successful that it was institutionalized after the war through the creation of organizations like the Defense Advanced Research Projects Agency, DARPA, and the National Laboratory System. The underlying philosophy remained consistent. Identify critical technological needs, apply the best scientific minds to solve them, then engage industrial partners to manufacture solutions at scale. For Germany, the lessons were equally profound, but learned too late. After the war, captured German scientists and engineers expressed amazement at American manufacturing capabilities. Wernher von Braun, whose V-2 rocket program had consumed enormous resources for limited military impact, remarked, "We had better scientists than the Americans, but they had better systems for turning science into practical technology." The proximity fuse exemplified this difference perfectly. The German wonder weapons approach, pursuing technological leaps that promised to overcome material disadvantages, proved fundamentally flawed. The V-2 rocket, the Me-262 jet fighter, and advanced submarine designs were all technological marvels, but none could be produced in sufficient quantities to affect the war's outcome. Albert Speer reflected on this failure in his post-war writings. "We failed to understand that modern warfare is fundamentally industrial rather than heroic. A technically superior weapon produced in hundreds cannot prevail against a good weapon produced in hundreds of thousands." Beyond its impact on World War II, the proximity fuse represented the dawn of a new technological era, the marriage of electronics and munitions that would eventually lead to smart weapons. The basic concept of the proximity fuse, using electronic sensing to improve weapon effectiveness, would evolve into laser-guided bombs, infrared-seeking missiles, and eventually autonomous weapon systems. Dr. Ralph Baldwin, one of the key proximity fuse scientists, observed in 1975, "What we created was the first smart weapon, a device that could make its own decisions about when to detonate based on sensing its environment." Every guided missile and smart bomb developed since has followed this fundamental approach. The societal impact extended beyond military technology. The manufacturing techniques developed for proximity fuse production, particularly the mass production of miniaturized electronic components, laid groundwork for the consumer electronics revolution that followed. Many of the companies involved in fuse production, including Raytheon and RCA, became leaders in early computer and television manufacturing. For individuals who worked on the program, the experience proved transformative. Mary Johnson, who assembled proximity fuses at the Crossley plant, reflected 50 years later, "Before the war, I was a housewife with a high school education. After working on the fuse program, I understood that I could master technical skills I never imagined possible." Thousands of women like me never went back to being just housewives after learning what we were capable of. The most profound legacy may be philosophical. The proximity fuse represented a uniquely American approach to warfare, using technology and industry to minimize risk to American lives while maximizing military effectiveness. Rather than accepting enormous casualties as the inevitable cost of war, American leaders sought technological solutions to reduce those costs. Admiral Lewis Strauss articulated this philosophy in 1945. "America's greatest military asset is not our raw materials or manufacturing capacity, but our ability to apply the full spectrum of human ingenuity to warfare." The proximity fuse exemplifies our refusal to accept that warfare must be conducted by traditional means regardless of the human cost. In the decades following World War II, proximity fuse technology continued to evolve. Modern versions use solid-state electronics rather than vacuum tubes and incorporate sophisticated signal processing to distinguish between targets and background. Yet the basic concept remains unchanged, using electronic sensing to determine the optimal moment of detonation. The story of the proximity fuse and its impact on German perceptions of American capabilities reminds us that technological advantage in warfare is rarely about a single breakthrough device. Rather, it emerges from the systematic application of scientific knowledge, engineering skill, and industrial capacity to solve specific military problems. As former Nazi armaments minister Albert Speer wrote in his final assessment, "The proximity fuse symbolized everything we failed to understand about American power. It wasn't just their factories or resources, or even their scientific knowledge. It was their ability to organize all these elements into a system that could routinely transform laboratory concepts into battlefield realities faster than we could comprehend, let alone counter." The stunned faces of German scientists examining captured proximity fuses in that Berlin laboratory in 1944 marked more than a moment of technical revelation. They represented the recognition that Germany had fundamentally miscalculated the nature of modern warfare and the true source of American strength. It was not, in the end, a contest between German quality and American quantity. It was a new kind of warfare entirely, where quality could be mass-produced, where scientific ingenuity could be democratized through industrial methods, and where the distinction between sophisticated technology and mass production had been rendered meaningless. In that moment of revelation, as they held in their hands a device that their nation could comprehend but not replicate, Germany's technical elite confronted the true mathematics of defeat, not just in numbers of tanks or planes or men, but in the capacity to make technological miracles routine through the marriage of science and industry. It was a lesson that would reshape warfare for the remainder of the 20th century.